Welcome to the very first video of Curious Mind GATE-2013. In this video, we are going to learn to recognize the characteristics of a partial differential equation, that is, its order and its types, whether it's a linear or non-linear partial differential equation, using this question as a reference, which is from GATE 2013 MESET A, which asks about the characteristics of this partial differential equation, that is, its order and its types, whether it's a linear or non-linear partial differential equation. And to do that, we will consider an arbitrary exact differential equation as an example and try to recognize its characteristics, that is, its order and its types, whether it's a linear or non-linear exact differential equation. Then we will come to our partial differential equation to recognize those same characteristics. Since we all are very much familiar with exact differential equations, as we frequently encounter them and learn a lot about them at the end of our schooling time and also during the study of our engineering courses in the colleges and universities, but we don't encounter partial differential equations to that extent during those times. And the technical reason for this consideration is also the fact that both partial differential equations and exact differential equations are the types of differential equations with a difference of formula consisting of partial derivatives and the latter consisting of exact derivatives. But first, I would like our viewers to recall that an exact derivative is a derivative of a dependable variable, let's say y, with respect to an independent variable, let's say x. So the functional relation can be written as and the corresponding derivative, or more precisely say exact derivative of y with respect to x can be written as, now this is a first derivative of y with respect to x, or the order of this derivative is 1 because it is a first order derivative of y with respect to x. One important thing to note here is that in case of exact derivatives, there is only one independent variable, that is input variable, which is x, which can be varied, and the dependable variable, which is y, and the dependable variable, which is y, becomes the function of that independent variable x. On the other hand, in case of partial derivatives, there can be many independent variables, let's say x and t, which which are in this given partial differential equation with one dependable variable, let's say u, and this one dependable variable becomes the function of those independent variables. So the functional form of this partial differential equation can be written as, so x and t are the independent variables and u is a dependable variable. So the partial derivative of u, which is a dependable variable, with respect to say x, which is one of the independent variable, is given by this del u by del x. Now when we consider this first partial derivative, we assume that t becomes constant, and when we consider partial derivative of u, which is a dependable variable, with respect to t, which is another independent variable, and in this case x becomes constant, meaning when we consider partial derivative of u with respect to x, then we assume t becomes constant, and when we consider partial derivative of u with respect to t, then x becomes constant. And likewise, we can also write second order partial derivatives of u with respect to x and with respect to t. What we observed here is that the partial derivative is the derivative of a dependable variable with respect to any of those independent variables, by assuming that the rest of the independent variables become constant in the functional relation of multiple independent variables and one dependent variable, and that functional relation is this: u is function of x and t, where u is the dependable variable and x and t are the independent variables. And these are the first partial derivatives of u with respect to x and u with respect to t. And these are the second order derivatives and second order partial derivatives with respect to x and with respect to t. We can also write second order exact derivative of y with respect to x, and third exact derivative of y with respect to x. Now, the order of the first exact derivative is 1. The order of second derivative, exact derivative, is 2. And the order of third exact derivative is 3. Similarly, the order of first partial derivative is 1. The order of this partial derivative, first partial derivative, is also 1, and the order of second partial derivative is 2, and the order of this second partial derivative is also 2. We can write the orders of these exact derivatives. The order of the first exact derivative is 1. The order of second exact derivative is 2. And the order of third exact derivative is 3. And so on. We can write the orders of higher order derivatives in the same manner. Now, similarly, we can write the orders of these partial derivatives also. Let's write an arbitrary exact differential equation whose terms contain any form of combinations of constants x by first derivative of y with respect to x, second derivative of y with respect to x, and third derivative of y with respect to x. Note, the exact differential equation can contain any order of derivatives. We will only consider up to third order derivative in our exact differential equation. In this exact differential equation, we will begin by highlighting the order of each derivative present in it, using the fact that the order of a particular derivative is the number of times the dependable variable is differentiated with respect to the independent variable in that particular derivative. So let's write the order of third derivative of y with respect to x is 3. The order of this second derivative of y with respect to x is 2. The order of first derivative of y with respect to x is 1. The order of, of this first derivative of y with respect to x is also 1. The order of this second derivative of y with respect to x is equal to 2. And similarly, the order of this first derivative of y with respect to x is equal to 1. And the order of this third derivative of y with respect to x is 3. Alright. To find the order of this entire arbitrary exact differential equation, we will use the fact that the order of an exact differential equation is the highest order that any of its derivatives has. So, while looking at the highlighted values of orders of all the derivatives present in our exact differential equation, the highest value is 3, which is in the first term and in the last term. So this becomes the order of our exact differential equation, 3. All right. Similarly, We can find the order of the above partial differential equation in the same manner because it is also a differential equation. Though it is not exact, it behaves like one because we assume rest of the independent variables in it constant when we consider a particular derivative in it. Let's write the partial differential equation on the right side of the board. There we have it. Now we highlight the value of the order of each partial derivative present in this partial differential equation. When we observe the values of the order of each partial derivative present in this partial differential equation, the highest value is 2. So this becomes the order of this whole partial differential equation, right? Because we know that the highest value of the order of any of the partial derivative present in a partial differential equation becomes the order of that whole partial differential equation. Again, we come to our exact differential equation on the left side of the board and would try to determine whether this is a linear or non-linear exact differential equation. And to do that, we first need to recall that a linear exact differential equation is the one that never contains any of combination of y and its derivatives, including any of their individual functional form in any of its terms. In other words, an exact differential equation is known as a linear exact differential equation only if each of its terms only contains either y or dy by dx, that is first derivative of y with respect to x, or second derivative of y with respect to x, or third derivative of y with respect to x, and neither any form of their combination nor their individual functions. Otherwise, it becomes a nonlinear exact differential equation. Now, we, we will check each term of our exact differential equation to see whether that term is making the exact differential equation a linear or non-linear. The important thing to note here is that if any one term of this exact differential equation makes the whole differential equation non-linear, then the exact differential equation becomes a non-linear differential equation. Viewers might be wondering why go further to check other terms if we have determined that it is a non-linear exact differential equation. And the reason for this is to make viewers familiarize with the concept of linear and non-linear differential equation. We will check the first term, and in this term there is only third order exact derivative and no other combination with other derivatives or with by, or there's no functional form of by or any of its derivatives. So this term is making this whole exact differential equation a linear differential equation. Now we move to the second term, in which there is a function of by u with power by, and in multiplication there is a second order exact derivative of by with respect to x. So there is a combination of functional relationship of by and second derivative of by in the second term. So this term is making this exact differential equation non-linear differential equation. We come to the third term, in which this first derivative of by with respect to x, but it is in a functional form because it has a whole power of 2. So this term is making exact differential equation a non-linear differential equation because dy by dx is not in an independent form in this term. Rather, it is in a functional form because it has a power of 2. Now come to the fourth term, which is this 5 multiplied by with power by 3. Here by has a power of 1 by 3. So this term is a functional form of by, and by is not here in an independent form, rather it is in a functional form. So this term is making this exact differential equation a non-linear differential equation. Alright, now come to the right side of the equality. The first term is x with power 3. Now there is no y or its any of its derivative or any of their functional form. So this term is making this whole differential equation a linear differential equation. Alright, the second term is by, which is in an independent form and not in a combination of any of its derivative, or and by is not also in a its any of its functional form. So this term is also making this whole exact differential equation a linear differential equation. All right, and we come to the third term, where there's a multiplication of two derivatives, first and second order derivatives. So this term is making this whole exact differential equation a non-linear differential equation because this term contains two derivatives of different orders in multiplication form. I mean, this term contains combinations of derivatives. All right. So this term is making this whole differential equation a non-linear differential equation. Uh, we come to the fourth term, which is cos by, and this term is actually a function of by, and here by is not in an independent form, rather it is a functional form. So this term is making this exact differential equation a non-linear differential equation. We come to this fifth term, which is by multiplied by dy by dx, and this term contains by and multiplied by dy by dx. So here is a combination of by and its derivative. So this term is making this whole exact differential equation a non-linear differential equation. Alright, now we come to the sixth term, which is a constant, and only a constant term makes an exact differential equation a linear differential equation, because this constant term does not contain by and any of its derivatives or their combinations or any of their functional forms. So this makes this whole differential exact differential equation a, a linear differential equation. Now we come to the seventh term, which is by with power 3, and here by is in a functional form because by is not in a independent form, rather it is in a functional form with a power 3. So this term is making this whole exact differential equation a non-linear differential equation. So we come to the last term, and here is a third derivative of y with respect to x, which is not in an independent form, rather it is in a functional form. Why? Because it has a power of -3. So this term is making this whole exact differential equation a non-linear differential equation. We have highlighted which term is making this whole differential equation linear and which term is making this whole differential equation non-linear. And as we can see that second term, third term, fourth term, third term after the equality, fourth term after the equality, fifth term after the equality, and last two terms are making this whole differential equation non-linear. But we do not need to check all the terms. If only one term makes the whole differential equation non-linear, then the whole differential equation automatically becomes the non-linear differential equation. So this is a non-linear differential equation with order 3. Now we move to the right side of the board to determine whether the partial differential equation is a linear or a non-linear using the same concept and process that we have used for the exact differential equation on the left side of the board, because both are differential equations resulting in the same characteristic behavior when it comes to linearity and non-linearity. We will check each term of the partial differential equation to see whether that term is making the whole partial differential equation a linear or non-linear. The important thing to note here is that if one term of the partial differential equation makes the whole partial differential equation non-linear, then the partial differential equation becomes a non-linear partial differential equation. So we will begin from the first term, which is first partial derivative of u with respect to t, and there is no combination with u and any functional form of u and any of its partial derivatives with respect to x and t in this term. And what we have here is only a single partial derivative of u with respect to t. So this term is making this whole partial differential equation a linear partial differential equation. And the second term, which is a combination of u and its partial derivative with respect to x. So this term is making this whole partial differential equation a non-linear differential equation, because this term contains a combination of u and its derivative and its partial derivative with respect to x. So this term is making this whole partial differential equation a non-linear partial differential equation. The first term on the right side of the equality is a second partial derivative of u with respect to x, and it is in an independent form in this term with no combination with any of other partial derivatives or with u, and nor any functional form with any of the derivative or with u. So this term is making this whole partial differential equation a linear partial differential equation. All right. Why? Because this term only contains a second order partial derivative of u with respect to x, and not any combination with u and any other derivatives, nor any functional form of those derivatives or of u. Right. So this term is making this whole partial differential equation a linear differential equation. So the second term is making this whole partial differential equation non-linear, while other two terms are making this whole partial differential equation linear, but the second term is making this whole partial differential equation non-linear. So this partial differential equation becomes a non-linear partial differential equation with order 2. So the correct option is D. The given partial differential equation is a non-linear equation of order 2.